decides what the amount of excitation current is. Normally, let's say in normal operation, this is done automatically. You can see the windings are put in here, in the gaps of the rotor. Here are the holes for the cooling media. And yeah, of course, the plus and the minus pole, the windings have to be connected. At the plus and the minus pole, that you can see here. Yeah, so here's the separation of the two poles. This is one pole and this is the other pole. And you can see in this case we have 1, 2, 3, 4, 5, 6 winding connections. And here you measure normally also the temperatures of the windings. And when you, later on, when you are in the plant, when you have a picture of your generator, normally you can see also these rotor temperatures, the winding temperatures. And normally they are not numerized with numbers, but they are numerized with letters, beginning at the inner winding. The inner winding would be A, the next would be B, C, D, E, F.
Measure everyone?
Sorry?
Both measure everyone?
Yes, yes. So you have a picture where you can see winding temperature A, B, C, D, E, F. Because you can have, in an emergency, you also can have unbalances. So you can have different temperatures of the windings, maybe.
Must be one winding.
Yeah, they are connected. Yeah, they are connected.
Why I bought 6 RTD or BTV?
Because then you that's better for the magnetic field when you have 6 windings. Yeah, you don't only have 6. Yeah, on the other side there are 6 windings more. Yeah, so you have 12 in this case per pole. Yeah, you have 1, 2, 3, 4, 5, 6, 7, 8, 9,
Yes,
10 on the other side.
I ask you about temperature measurement.
The measurement.
Yes, so why I bought 6 BT to take this measurement?
You would only take one measurement.
One
or what is the question? So you would only take one measurement, or what was the question? Your question was, why do I take 6 measurements?
Yes.
Because you also can get unbalances. Because the temperature of the winding depends on the current that's flowing over the winding.
One current, one winding. One winding.
Yeah, one. Yeah, how should I call it? One conductor, which is going through the rotor.
One coil. Coil.
Yeah, the coil is this. Yeah, but this is a straight line, a straight conductor which is going on the side of the conductor.
Yes.
That's what I call winding. That's the normal, also the normal, let's say, word for this. You also have stator windings, which are going through the stator. That's a winding. So when maybe this conductor here has another current flowing as this one, then it has another temperature. So by measuring the temperatures, you can see unbalances. So when one winding has a higher temperature than another, then you have an unbalance. So that's why you measure all 6. Yeah, we can briefly go over this. This is the solid pole generator again that we saw before already, but now in a whole picture. You heard this, what we call this. Yeah, this is the wedding, where the rotor goes into the stator. And here you can see the solid poles. Yeah, so this generator has 4 poles. Yeah, this rotor, 1, 2, 3, 4 solid poles. Only for small generators. Yeah, you can see this is a small generator for an industrial plant. Yeah, you will not see this in a big power plant. Yeah. Because when you rotate this with 3,000 rotations per minute, you can imagine that this gap is causing unbalances in the rotation. Yeah, this is a hydroelectric rotor. You can see this one has many poles. We talked about this hydroelectric generator. When you only have 500 rotations per minute, we said you need 12 poles on the rotor to get 50 Hertz. Okay, so so that is the main setup. Yeah? You have a stator, you have a rotor. On the rotor you put your direct current for the magnetic field, and on the stator the voltage is induced that you need for your grid. Now what comes now is, also as we had it at the transformer, we talk a little bit about losses. What losses do we have and what is the result for our operation? What do we have to have as systems? And then we will talk about the auxiliary systems that we need. Yeah, we had the generator itself, and then after that we will talk about the auxiliary system, seal-oil system, hydrogen supply, because your generator is cooled with hydrogen, and the excitation we had already. What is your excitation? Okay, what losses do we have? Of course, we have current losses, just like at the transformer. We have current losses at the stator windings and at the rotor windings. And of course, also as at the transformer, the current losses are load dependent, because the current that flows depends on the load that you have. Then you have got friction losses in the bearing, of course. You have many bearings, not only at the generator, but also at the turbine. The turbine also has some bearings. And you have ventilation losses. What is meant by ventilation losses in the generator? Hydrogen, of course. Hydrogen is meant by this. Please again, I didn't understand. The cooling media is driven into the gap between rotor and stator. But the H2, the hydrogen, doesn't do you the favor that it's flowing straight in one line. But it's doing this. There are turbulences in the flow. And these turbulences, they cause losses. These turbulences, and that is called ventilation losses. These turbulences that the cooling media makes. Approximately 40% of the total losses are ventilation losses. But we cannot do really anything about it because we need the cooling media. So we have to live with these losses. What you can do is you can choose the right cooling media because, as I said, up to an apparent power approximately 250 MVA, you can use air as cooling media inside of the generator. And 250 MVA. You have a bigger generator. Your generator has 450 approximately MVA. And there, air is not enough to put the heat out of the generator. There you need a media which has a higher heat capacity. But these ventilation losses also depend on the media that you use because the gases have different densities. Hydrogen is lighter than air, so hydrogen has also lower ventilation losses. And that's also an advantage that you have with hydrogen. Lower ventilation losses than with air. These ventilation losses and friction losses are rotation dependent. So how fast you rotate. So in normal operation, they are constant because you rotate with 3,000 rotations per minute. Bearing and ventilation losses. Then we have eddy current losses, of course. We have the laminated plates in the iron core, but we cannot, let's say, delete the total eddy current losses. We have some eddy current losses. And we have some losses for remagnetizing because we have the rotating magnetic field. And this has not the same strength at every position. So we have some losses for remagnetizing of the iron core during the rotation. What do we have to avoid during operation? We have to avoid high temperatures, of course, inside of the generator, because then we have too much heat. High temperatures means we have too much heat, too much current. Also, the insulation material would be damaged with too much heat. Too much heat means, okay, it's too much heat that our cooling media cannot put away outside of the generator. What can we do? Does somebody know when we have too high temperatures inside of the generator? What can we do as an operator when we have too high temperatures inside of the generator?
Decrease the load.
Decrease load.
Check the cooling system.
Yes, check the cooling system. Some plants are able to maintain the hydrogen pressure. The normal, a little bit. We will see that in the capability curve later on. Not today, but maybe tomorrow. Or inshallah. The normal hydrogen pressure in your generator is 5 bar. So you have to maintain a pressure of 5 bar. But if you would be able to increase the hydrogen pressure maybe to 6 bar or to 5.5 bar, then you have better cooling. So if you are able to do this, then you can also increase the hydrogen pressure. We will see that in the capability curve later on, because there are limit curves in the capability curve, and some of them depend on the hydrogen pressure. We have to avoid low temperatures because of humidity. You could say, okay, we have hydrogen in our generator, where should the humidity come from? But I think you know this, you don't have 100% hydrogen inside of your generator. That's not possible in nature, that you have 100% of anything. So you have a little percentage of other gases also inside of your generator. We say normally you should have a purity, this is called purity of hydrogen. You should have a purity of 98, approximately 98%. So that you have 98% hydrogen and 2% of other gases inside of your generator during operation. But inside the 2% of other gases, there could be humidity. So we have to avoid low temperatures, because then the humidity could come out of these gases. Some also operate with a lower purity, 95 or 96% of hydrogen.
What do you mean by humidity?